Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. Today's lecture is the continuation of the previous lecture. In the previous lecture, we have started with the derivation of Reynolds transport theorem. Reynolds transport theorem, we have seen the introduction part of it, and the Reynolds transport theorem relates the time rate of change of extensive property within the control mass or system to the reasons behind these changes. That is, the reasons which are causing the changes. So, yesterday we have, in the previous lecture, we have started with the derivation, and the expression came out to be like this. We have considered a fluid flow field. Within that, we have considered a control mass, and for the analysis point of view, under the Eulerian perspective, we have considered a control volume. At time t, this control volume and the system were coinciding each other. After a small interval of time, delta t, the system has moved to the right hand side, that is in the flow direction, and we were trying to find out the relationship with the time rate of change of extensive property. Whatever be that extensive property, time rate of change of extensive property within the system to that of a control volume. So, let us continue from the point where we stopped yesterday. Time rate of change of extensive property of the system is related to two terms. First term was something related to the control volume, and the second term was something related to the control surface. That is, you can see here, this is B2 at time delta t tends to 0, region 2 is coinciding with the control volume. So, B2 t plus limit delta t tends to 0, 1 by delta t B2 t plus delta t minus B2 t was found out to be time rate of change of extensive property stored within the control volume. So, this term we have derived yesterday. Now, we have to move on with the second term. This is the expression representing time rate of change of extensive property within the control volume. Now, let us look into term 2 in detail. Here it is in terms of extensive property B3, B1, etc. So, that we need to write in terms of intensive property. So, again the same figure is depicted here, and term 2 we are going to look into in detail. So, here we are having B3, that is region 3 and also region 1, both are representing the outflow and inflow control surfaces. B1 and B3, the flow of the regions, extensive properties in regions 1 and 3 across the control surfaces. So, this involves the inflow and outflow regions. Now, what we are going to do, we are going to look at this control surfaces in a closer way. That is, let us see the expanded view of the outflow region first. So, this is our control volume that we have seen earlier at time t is equal to 0 and t is equal to t and all times. And control mass of the system was coinciding with this control volume when time t is equal to t, and the time is increased to T plus delta T, system has moved to the right hand side represented by these pink dots. Now what we are going to do, these are represented by region 2 and region 3. We will consider an area dA, here you can see dA in the outflow control surface. So area is a vector, so area will be having a direction. The direction of an area will be taken always in the outward normal direction. So that is marked with vector n. Then we need to consider the volume of tube containing all the fluid passing through dA in time delta t. That is represented by the notation dV. So that is depicted here with the help of this green solid diagram, which is having a length of delta L. And here you can see I have marked the velocity vector. So velocity is in the flow direction, this is marked as V. We are considering an angle theta, which is the angle between the velocity vector and the normal to the area vector. So we are going to consider angle theta, which is the angle between velocity vector and the direction n normal to the area element dA. So this is the tube which is containing the fluid in the control surface or in the outflow region, which is having a length of delta L. Area vector is in the direction marked in the direction of unit vector n, and the velocity vector is in the flow direction. The angle between these two are represented by theta. What we are going to do is to get the expression for volume. So the length of the elemental tube or the length of the flow path in time delta t, that is delta L, that delta L is nothing but velocity multiplied by delta t. V into t will be giving you the distance travelled, length of that particular tube. So we can get delta L by taking the expression V delta t. V is nothing but a velocity. Now coming to the expression for volume. This is a solid tube in which the flow is taking place. So the area, the volume representing corresponding to this particular tube will be base area multiplied by the perpendicular distance between these two faces. So what will be the value corresponding to that perpendicular distance? So dV is given by base area into perpendicular height. So base area is nothing but our small elemental area dA. So dV can be written as dA multiplied by delta L cos theta. So this is the slanting length of the fluid element delta L multiplied by this angle is theta. So this angle also will be theta. So we can consider the component in the direction as delta L cos theta. So the volume of the tube can be obtained by using this expression dV is equal to dA delta L cos theta. Now we need to get the expression for extensive property in the tube across the control surface, which is there in the outflow region, that is region 3, that is beta rho dV. We know the expression is beta rho dV. Here what we are going to do, we are going to substitute for dV. The expression for dV we have already found out. So that we will substitute in the expression for amount of extensive property B. It will be coming out to be beta rho delta L cos theta dA. This is corresponding to an elemental volume. This expression we got after considering a small elemental area dA, and the corresponding volume dV, elemental volume we have calculated, and based on that, for that elemental tube which contains the flowing fluid was having a volume of delta L cos theta dA, and based on that we calculated the extensive property corresponding to that small elemental area. So, the total amount of extensive property B leaving through the control surface in the region 3, outflow control surface, will be definitely we need to integrate this over that particular area. It is across the control surface. So, we will be integrating over that area. So, B3T plus delta T will be given by surface integral of beta rho delta L cos theta dA. This is corresponding to the outflow region. So, we are having it for region 3. So, we got the expression for the total amount of extensive property B leaving out the control surface as B3T plus delta T. Now, in the similar way we need to find out the expression for fluid element or the matter which is entering into the control volume. So, for that we will be considering the inflow region, that is region 1. So, we will see the expanded view of inflow region. So, this is our inflow region. At time t is equal to t, we are having the control volume and system coinciding each other. After delta t time, system has moved in the flow direction, that is marked by the pink direction. So, this is region 1 and we are having the region 2 which is contained by the control volume and the system. So, within the region 1 we are going to consider an elemental volume which is having an area dA and length, which is having a cross sectional area dA and length delta L. Now, again in the similar way what we have done for the outflow region, we are having the direction vector corresponding to area dA in the outward direction, that is marked by this unit vector n, and the velocity direction is in the along the flow direction. How the flow was taking place? Flow was taking place from left to right. So, the velocity vector will be in the flow direction. So, here you should understand that the direction vector corresponding to area and the velocity both are in the opposite direction. And the angle between these area vector and the velocity vector is represented by theta. Now, the similar analysis will be carried out for the region 1 also, that is for the fluid entering to the control volume. So, this is our small area which is having small elemental volume which is having a length of delta L, velocity is in the flow direction and we are having the area normal to the cross section dA, and the angle between the area vector and the velocity vector is represented by theta. Now, we need to calculate the volume of the tube containing all the fluid passing through dA in time delta t. So, the same expression will be used, that is volume delta V, dV is equal to area cross sectional area multiplied by the perpendicular distance between both the faces. So, here also dV is equal to dA multiplied by what will be the component of length, that is delta L, this horizontal distance we need, perpendicular distance we need. So, this delta L cos, what is the value corresponding to theta? Theta is less than 180 degrees. So, it will be 180 minus theta, delta L cos 180 minus theta. So, what is cos 180 minus theta? It is minus cos theta. So, the expression for dV in the inflow region is having a negative sign. So, it will be minus delta L cos theta dA. Now, the same procedure we will do for the inflow region also. Amount of extensive property B in the tube across the inflow control surface is given by beta rho dV, and then we will calculate the total amount of extensive property which is entering the control volume. So, total amount of extensive property, here we have substituted for dV we have substituted delta L cos theta dA. Now, we need to get the total amount of extensive property. Total amount of extensive property will be the integral of this particular quantity. that is given by minus of surface integral beta rho delta L cos theta dA. Negative has come due to the angle. Angle was 180 minus theta, cos of 180 minus theta is minus cos theta. So, this is across the controlled surface represented by region 1, inflow control surface. This is the net amount of extensive property through the entire control surface in region 1. So, we got the expression corresponding to control surface representing region 1 and also region 3, that is the inflow region and also outflow region. Now, we can substitute corresponding to term 2. So, we are going back to our Reynolds transport theorem expression which we have derived for Reynolds transport theorem. Time rate of change of extensive property within the system is related to some property related to control volume, and we are having the term 2 here. So, the expressions corresponding to B3 T plus delta T, B1 T we have already found out. So, now we will substitute in term 2, that is the expression for B3 T plus delta T, and B1 T we will substitute in term 2. So, term 2 is limit delta T tends to 0, 1 by delta T, B3 T plus delta T minus B1 T is equal to limit 1 by delta T. What is the expression for B3? B3 is given by this surface integral, and B1 is given by this expression, that is substituted here, and we got the expression for the term 2 in the RTT. So, here you can see limit delta T tends to 0, 1 by delta T of this entire term. Both this sign was negative here, it has become positive because we got the value corresponding to inflow region to be negative. Negative and one negative sign here, together it will be positive. Now, we need to modify this expression because we are having the limit delta T tends to 0, 1 by delta T. In the next step we will do that. So, term 2 is this, and we have written the expression like this. Now, you look at the numerator, we are having delta L and denominator delta T. So, limit delta T tends to 0, delta L by delta T, what is it? Length divided by time, and at the same time delta T is tending to 0, it is nothing but the magnitude of the velocity. So, we can write limit delta T tends to 0, delta L by delta T to be equal to V. So, this expression we are modifying, limit has gone. Now, we are having the term 2 as surface integral beta rho V cos theta dA for the region 3 plus surface integral of beta rho V cos theta dA corresponding to region 2. Both the expressions are same within the integral, only the regions are different. So, we can express this term as a net outflow, that is some amount of fluid is entering the control volume and some amount is leaving the control volume. So, the summation of that was actually negative, minus was there, we were subtracting, because of the negative sign came for the inflow value, it has become positive. So, if we are summing up these two, we are getting the value corresponding to, that is the extensive property which is net outflow of extensive property, that is represented by this term 2. Now, we can modify that particular expression again. V cos theta dA can be written as the dot product of these two vectors. We know area is a vector, velocity is a vector, and cos theta is there. So, V cos theta dA can be written as V dot dA. So, this we will substitute in the previous expression, it will be modified like this, that is surface integral of beta rho V dot dA corresponding to outflow region and beta rho plus surface integral of beta rho V dot dA corresponding to inflow region. This is the expression for the extensive property that is flowing across the control surfaces. Now, what we have to do? We are having the expression for term 1 and also term 2, that will combine together, we will put it in equation 3, that is dB by dt of system is equal to, this is corresponding to control volume and this is corresponding to control surface. We are having separate expressions for these two terms that we are going to substitute in equation 3, that is dB by dt of system is equal to d by dt of beta rho dV within the control volume plus beta rho V dot dA corresponding to region 3 and region 1, that is corresponding to the control surface. So, this is dB by dt system. It is the time rate of change of extensive property within the system due to some external factor that we do not know what is creating this change. And first term on the right hand side is the time rate of change of extensive property stored within the control volume. And last term, these two terms together which are representing the flow of extensive property across the control surface, that is from the outflow and inflow region. These two can be combined together. I am removing the region 3, region 1 notation and together I am putting across the control surface. So, you can write the expression for Reynolds transport theorem like this: time rate of change of extensive property of system is equal to time rate of change of extensive property stored within the control volume plus extensive property that is flowing across the outflow and inflow region. So, this is the mathematical form of Reynolds transport theorem. Now, we need to look at this equation for understanding the relationship. Initially itself I told you what Reynolds transport theorem is doing. Fundamental laws are derived based on Lagrangian approach. So, we are tracing a single particle, individual particle for understanding the flow characteristics. But majority of the engineering problems, it will not be feasible. So, that case here what we are doing, what RTT is doing, RTT is trying to relate the quantities which we got based on the Lagrangian approach to that of the one using Eulerian approach. So, it relates the time rate of change of dB by dt to the external causes producing this. We got the expression for this in mathematical form, that is it has two parts. One is the time rate of change of extensive properties stored within the control volume, and second part is the net outflow of the extensive property across the control surface. I am rewriting it again. dB by dt of system is equal to d by dt of beta rho dV across the control volume plus surface integral of beta rho V dot dA across the control surface within the control volume and across the control surface. So, left hand side, this associates the time rate of change of extensive property of a system. You look at the left hand side, it is something related to system. System concept means it is based on the Lagrangian approach. And look at the right hand side. Right hand side is we are having something related to control volume. Control volume approach is based on the Eulerian approach. So, it associates the time rate of change of extensive property of a system, that is for a system it is the control mass to the rate of change of same property within the control volume and the net outflow of extensive property across the control surface. So, you can see dB by dt system is based on Lagrangian approach and d by dt of beta rho dV within control volume is based on Eulerian approach. So, here you can see we have considered the system, what are the changes taking place in the extensive property, as time changes from t to t plus delta t, that is dB by dt. So, this based on this Lagrangian approach we are having the fundamental laws, and we have found out the relationship between the Lagrangian approach and the Eulerian approach. So, we can make use of the fundamental laws based on Lagrangian approach for engineering problems which we deal by using the Eulerian approach. Now, some properties we need to understand related to this particular theorem. That is, we are having the control volume, control surface. Term 2 is representing the flow across the control surface. So, we need to understand how the control surface is behaving. You can look into our figure that is given by this figure, the figure which we have started with. So, here you can see this region and this region both are impervious boundaries. We were having the flow from left hand side to right hand side through this inflow and outflow regions. So, at impervious boundaries, when we take V dot dA, this will be equal to 0. Okay, V dot dA will be equal to 0. That is, there is no flow of extensive property across the impervious boundary. Definitely we know. That is, if it is impervious, it will not permit any flow to take place through that boundary. Now, for inflow and outflow region, we have seen that for inflow region, it will be between 90 and 270. So, theta, cos theta will be negative. And in the case of outflow region, theta is less than 90 degrees, so it will be positive. So, depending on the flow direction, the angle will be different. For this particular case, I have written flow direction is in left hand side to right hand side. If it is the case of a river from upstream to downstream, in the case of hydraulics channel cases, open channel cases, it is from upstream to downstream. So, in that case, if you are considering for the inflow region, always the area, when we consider area vector, will be pointing in the outward normal direction. Flow is in the direction from upstream to downstream. So, for the inflow region, it will be angle will be between 90 and 270, and in the case of outflow region, it will be less than 90. According to the angle, what is the angle corresponding to a particular problem, based on that, that particular term will be positive or negative. So, here we got the inflow region to have a negative sign and outflow to be positive. And in the case of impervious boundaries, this thing should be very clear to you, V dot dA will be 0. So, this particular theorem, derivation, basics related to this, all this I have taken from the textbook of Applied Hydrology by Bente Chow and others. So, we have seen the detailed description about the Reynolds transport theorem in these 3 lectures. We have started with the introduction of Reynolds transport theorem. In that we have seen the basic fluid properties which depends on mass and which are independent of mass, that is extensive and intensive properties. Based on that, we have started the Reynolds transport theorem, and it related, in that we have seen both the approaches, Lagrangian approach and also Eulerian approach. Lagrangian approach, we are considering a control mass, Eulerian approach, we are considering the control volume. So, once we derived the expression, we found the relationship between the time rate of change of extensive property within the system to that of control volume. So, this theorem can be, this is a mathematical expression we have seen. This theorem can be utilized for deriving the basic laws based on Eulerian approach. Actually, what we are doing, we are relating this thing to the control mass Lagrangian concepts. So, based on this RTT derivation or the equation which we got, we will derive the basic conservation laws based on Eulerian approach. Here I am stopping for now. Thank you. Have a nice day.